Hi, here we discuss about a project, a 25 Mbps per second 4 ASK receiver front-end in 65 nanometer CMOS for biomedical data telemetry via a capacitive link. Here, the wireless biomedical implements are increasingly used in applications such as neural monitoring, health sensing, implant programming, where the fast and reliable data transfers with a low power consumption is essential. Here, the capacitive based wireless link offers advantages such as a high bandwidth, improved biosafety, and better tolerance to tissue properties compared to the inductive and RF link, and making them suitable for high speed implant communications. However, this link suffers from the signal attenuations and distortion through biomedical tissues and challenges in accurate with the clock and data recovery when multi-level modulation schemes are used. From this existing ASK, traditional and conventional clock and data recovery circuits are mainly designed for binary signals and often experienced a high error rate, increased jitters, and unreliable operations when handling a weak multi-level signals under varying conditions. But the recent systems will have an additional synchronization link with the complex architectures or often required. It's also having increased power consumptions and system complexity. To address this limitation, this work proposes a low power, high speed ASK receiver front end using a capacitive link and capable of reliable recovering both data and clock from the signal receiver method. The proposed designs converted the receiver ASK waveforms into a stable pulse amplitude modulation, which means a PAM 4-digit level, and employs a improved clock and data recovery architectures with a highly linear transconductance based phase detector, and to enhance the phase detection's accuracy and reduce jitters. Okay, and adaptive biasing techniques are used to maintain a linear operations over a wide range input with improving robustness against the tissue induced signal variations. The novelty of this work lies in the combinations of PAM4 based CDR operations and a highly linear phase detections approach with optimized for biomedical capacitive link. Here, the proposed receivers is evaluated through circuit level simulations using Tanner EDA at 45 nanometer CMOS technology and validated using a realistic operating conditions, also demonstrating a low power consumption and improved signal integrity and stable clock recovery and reliable high-speed performance suitable for implantable biomedical applications. Now we can verify the paper. So this paper is fully designed for the 4 ASK receiver modulation with support of the capacitive link based biomedical data telemetry. Okay, so here we can verify the core architectures. This is the architectures. Okay, so initially we design with the message signal, and after that the carrier signal, and after that the message signal merged with this carrier signal and also created a amplitude modulations. Okay, ASK, amplitude shift keying based modulation signal. Okay, and that signals it will be given to the VIN. Okay, so here this one it will become with the 4 ASK architectures. Okay, which means of the 4 reference input voltage they will be used to recover the signal. Okay, so once they recovered it, after that it will be converted into the pulse based signal. Okay, so this graph it will be shown here. Okay, so this is a pulse amplitude modulations. Okay, so the 4 number of pulse amplitude modulation signals they will be recovered, and after that it will be sampled. After that it will added into using the full adders. Okay, and it will given to the driver circuit. Okay, and this figure 3 is a PAM4 CDR block diagram. Okay, so this is a continuation circuit from the figure 2. Okay, 4 ASK to 4 PAM. Okay, so here this architecture it will predict the DN and it will change the pulse amplitude modulation to the recover signal. Okay, with support of this data transmission detectors, up down logic, and CP and PD1. Okay, and data extensions and phase detectors. Okay, so below some architectures they will be given the detailed functionality. Okay, so here the figure 4 it will be showing for the PD architectures. Okay, so here the PD architectures, it will be taken the data and it will operating with a transconductance functionality, which means that the GM minus 2 GM. Okay, after that it will compare the data and finally it will generate the CP. Okay, so here the figure 5, it will be showing for the linear transconductance architectures. Okay, which means the GM and the control signal for this pulse amplitude modulations. Okay, now this work we designed in Tanner EDA at 45 nanometer CMOS technology. Okay, so these are the test bench verification signals. Okay, and this is the testing. Here it will be come with a 45 nanometer CMOS method. Okay, and this is a core architecture for ASK signal generations. Okay, so here we created a 500 kilohertz for testing verification signal. Okay, so that is a carrier signal, and after that we created a message signal. Okay, so here the two signals, it will be merged with here. Okay, so that is the ASK signals, it will be generated here. Okay, after that the ASK signal we given input to the ASK receiver model. Okay, so this is a core of this paper. Okay, so here this one is a ASK2 pulse amplitude modulation and this one is a CDR loop. Okay, so initially we seen that this ASK2 pulse amplitude modulation, it will present with a comparator and a buffer, and after that the similar architecture. Okay, so initially we refer the signal with support of this reference 4 reference voltage, that is a 4 ASK signal configurations. Okay, after that it will convert the data into the pulse amplitude modulations in support of this similar architectures. Okay, so this similar, it will convert the signals to pulse. Okay, after that we added the signal and after that we taken as a data driver output. Okay, and this is a receiver part. Okay, so here this model, it will generate the P data and N data. Using this P data and N data, this pulse amplitude modulation is also required for the reference input. Okay, so using the support of this references, it will created GM cells. Okay, and the data transfer detectors and the charge pump architectures. Okay, so and then it will ready for the simulations. Okay, so once we execute this work at 45 nanometer CMOS technology and 0.8 input voltage. Okay, so we will get this type of signals. Okay, so here you can analyze the pulse amplitude modulations and carrier signal and message signals. Okay, so initially the first signal will be start with the message signal. Okay, and after that the carrier signal. So this two signals we merged in the ASK generator. Okay, and this one is a modulated signal. Okay, so this one is a final recover signal. Okay, okay, so here the message signals will be taken here. Okay, and recover signal, it will be taken here. Okay, and this work we compared it. Okay, so here delay it will be take for 1.03 e power minus 5. Okay, and file open folder containing TB, we verified the log file. MOSFET will be take for 680. Okay, and power consumptions, it will be taken with 1.1926. Okay, so this all details, it will be compared the existing 65 nanometer from the paper architecture. Okay, so this is a comparison table, and finally we written abstract document, title, base paper abstract, objective of this work, proposed title, proposed abstract, and related notes for this project. Okay, finally we come up with the literature survey and references. Okay, thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.
Introducing NXFE Innovation, your trusted partner in IP design and VLSI research. With over 300 plus completed projects in cutting-edge domains like low-power VLSI design, high-speed data transmission, signal processing, and secure networking. We offer tailored solutions for students and professionals in BE, BTech, ME, MTech, and PhD programs. At NXV, you not only get expert-guided projects starting from RIS 6000 Transparency, but also enjoy unmatched benefits like RIS 1000 to off on your second project, free documentation, and easy-to-understand video explanations. Plus, our rewarding referral program lets you earn up to RIS 2000 MANTs for every successful referral. Trust us to simplify your research journey with high-quality, affordable, and fully customized VLSI solutions. Visit our website to explore a comprehensive collection of projects, organized year by year from 2014 to 2024. The latest 2024 research projects are now available for publication, along with several 2024 non-completed titles, which are updated monthly with new possibilities. For application-based projects, interface designs, and mini projects, you can also rely on NXV for top-quality solutions. We provide exceptional PhD assistance with full publication support and offer an installment payment option, allowing you to pay module by module. Let NXV guide you through your research journey with flexibility and expert support. Thank you.